Ready now then? So today's speaker is Campbell Wheeler, and the title is Difference Equations and Three Manifolds. So Campbell, please.
Thanks, Ian. So yeah, I want to thank Ian for inviting me to talk, and thanks everyone for coming. Yeah, so today I'm going to talk about difference equations and three manifolds and how solving certain difference equations associated to three manifolds seem to give rise to matrices of invariance. Although we don't have definitions for these invariants, it seems like something like this should exist. And so I'll give you some sort of structures that these kind of matrices compute and yeah, hopefully motivate a reason that we should look for a definition of these in some way. Okay. So I'll start off by giving a brief introduction to Q-difference equations, and then I'll talk about three manifolds, sort of quantum invariance of three manifolds, essentially. And then I'll go on to discuss the asymptotics of quantum invariance, and then hopefully yeah, go on to talk about conjectures for the Borel resummation for these asymptotic series and calculating their Stokes constants. And so this is all based on joint work with Stavros Garofalidis, Jib Gu, and Marcos Marino. And sort of the initial version of some of the calculations that I'll talk about are based in their joint work that was previous to our collaboration. And so I'll sort of talk about the analogues of some of their conjectures in the case of closed manifolds. So the main motivation is trying to understand quantum SL2C Chern-Simons theory in some sense. And so this leads to interesting asymptotic series, and to zeroth order, it knows about the volumes or hyperbolic volumes of three manifolds. Then we have a whole asymptotic series which stores interesting information. So these asymptotic series are conjecturally resurgent, and we'd like to be able to understand all of the sort of analytic structures associated to this when we attempt to resum these asymptotic series. And so, as I said, Garofalidis, Gu, and Marino came up with a picture for some simple knots, and their method for calculation, it completely generalizes to a very large class of Q hypergeometric series. And so in particular, we can apply these kind of methods to interesting Q series that are predicted from physics recently for closed manifolds. And I'll sort of talk about how these Q series are related to more classical quantum invariants like the WIT invariant for a closed manifold. Okay, so that's what we aim. And so, as I said, we want a matrix of invariants, and this matrix should solve a Q-difference equation. It should ratios of this matrix at different arguments in sort of for different arguments should give rise to the Borel resummation, and then a different ratio between different arguments should give rise to Stokes constants. So this matrix seems to store quite a lot of information if we could find a mathematical definition for it. Okay. Okay, so yeah, so let's start with Q-difference equations. So what is it? So we can take the quantum torus, or the Q-Weyl algebra, which is just defined as some algebra over Laurent polynomials, and we insist that, so it's an algebra generated by X and sigma, and we want these to Q commute. Okay, so we can think of Q as some formal parameter, or we can think of it, for most of this talk, I'm considering Q series, and I want Q to be less than 1, so some complex number less than 1. So it's a good way to think about it. This algebra naturally acts on functions in X and Q as follows. So X, we just multiply by X by some sort of abusive notation. And then here, sigma is just the shift operator. So we multiply X by Q. Okay. So yeah, this action is well defined. It's easy to compute. Here's the equation. And so then a Q-difference equation is an equation for some function f. So we want to solve a linear equation. So we take some polynomial in this sigma of order r with some coefficients, some Laurent polynomials, maybe rational functions in X and Q. So we could maybe extend this, not just have Laurent polynomials, we can extend slightly, but regardless. So we take some operator here and we want this to annihilate some function f, and this is an rth order Q-difference equation for f. Okay, great. And so you can think of this as defining some module over this non-commutative algebra. Okay. So the best way to solve Q-difference equations, or in one-dimensional linear Q-difference equations, for me, is to use the Newton polygon and just apply Frobenius's method. And so Frobenius gives an algorithm for constructing solutions to linear differential equations, and there's an analog in the Q-difference world. And so to sort of do this algorithmically, it's nice to construct this Newton polygon and sort of look at edges of this and construct solutions corresponding to edges of this polygon. So how this polygon is defined is if we have an operator of this form, so it's some polynomial in x and sigma, we can just choose this ordering. And so this A of KL is some, A of KL is just some function of Q, maybe some rational function in Q or something like this. And we look for this operator or this element of the Weyl algebra. We define its Newton polygon to basically just keep track of which of these AKLs are non-zero. Okay, so a simple example, if I take this operator, then if I look at the powers of sigma, so here sigma to the 2, and there's no power of x, so I get this point here. Okay, for sigma to the power of 1, I see there's one term that corresponds to x and one without, so I get these 2 points. And then for sigma to the 0, I just see an x. And so I get this point up here. And so we take the convex hull of this set of points. Okay, and so now when we construct solutions to the difference equation, we'll look at the bottom of the Newton polygon, and to each edge, we'll essentially construct some function that will satisfy this operator. Okay, so to apply Frobenius's method, unfortunately, you need to sort of fix some constants at some stage, and this is much worse in the Q-difference world because the constants for Q-difference equations are much larger. So in particular, if I have some elliptic function, so that's this, say, function g, such that the shift in Q is just equal to the unshifted version, then of course, if I multiply any solution to a difference equation by this function g, it will still satisfy the same difference equation. So this leads to many, many different conventions in a lot of these constructions. And so if you look, for example, for the definition of a Q-Laplace transform, I mean, yeah, there's many, many, many definitions, and this sort of all stems from this fact that constants now are a much bigger field. Okay, so you can kind of fix your conventions by choosing a particular solution to an equation. So in particular here, if I look at this equation, if I choose a solution to this, then this sort of dictates how I should follow through with all of my constructions when I try and construct solutions. And so here, the solution that I choose is just this theta function, because we'll look at sort of modular objects later, and this theta function has nice modular properties. So here you can write it as this infinite sum, and the Jacobi triple product identity says you can write it as this product of 3 Pochhammer symbols, where the Pochhammer symbol is defined as this product down here, and n can be infinity, of course. And so then to apply Frobenius's method, we take some ansatz. So for differential equations, you have some ansatz of this form. You have some exponential singularity with, this is a Laurent polynomial, we're solving around x. And so here we see some exponential singularity, essential singularity. And so we pull that essential singularity out in terms of this exponential. And then we get left with a power series with some sort of shifted indices. And so here we solve, when we look at the Newton polygon for the differential operator, somehow the P is determined by different slopes of the Newton polygon, and then this R will correspond to some polynomial associated to each edge. And so once we solve them, we can choose an alpha 0, and then the differential equation will give us a recursion for the rest of the alphas. And the same will work for Q-difference equations. Here, the exponential singularity is replaced by this sort of theta function singularity. And we saw previously that the theta function has this infinite dimensional sum, where there's infinitely many positive powers of x and negative powers of x. And so you can think of this as sort of an analog of the exponential singularity. And then here, this R, instead of, I could also do the k plus R here, but it's more natural because of my convention to take this product or this quotient of 2 theta functions. And so then this rho is somehow an analog of x to the R. And so here I take this ansatz, and the kappa is determined by slopes of the polygon, and then this rho comes basically by insisting that the alpha k for k less than 0 has to vanish. And so that gives you some polynomial equation for this rho, and you can solve this. If the polynomial has multiplicity, like if the root of this polynomial that determines rho has multiplicity, you take some formal expansion here. So in the differential equation world, this would correspond to sort of logarithmic solutions around your point. And so this is the analog in the Q difference world. Okay, so using this, we can at least just plug in this ansatz, we choose our kappa, we solve for our rho, and then fix an alpha 0, and then solve for the rest of alpha. And this will give us, we can then find a basis of formal solutions. These alpha might diverge. But regardless, when we find a basis of solutions, we can put them into a Wronskian of this form. And this Wronskian, when we have a Q difference equation coming from a 3-manifold, this is sort of we want to correctly normalize Wronskian in some way. This should be our matrix of invariance, but the correct normalization is the subtle point in general. But okay, so we want to construct these Wronskians, but it would be nice if instead of formal solutions, we had meromorphic functions here for Q less than 1. And so this can be done when we take our formal solutions and apply some sort of Q Borel resummation. So here it's actually much easier than in the differential equation world because the analytic continuation is much easier to calculate. But regardless, okay, so we have formal solutions that might be divergent, and we can Q Borel resum them. And this was proved like in the last 10 years, maybe 5 years ago or so by Dreyfus in a nice article, Tom R. Dreyfus. And so I'll give you a brief idea of how this Q Borel resummation goes. So sort of a kappa-weighted Borel transform with my normalization. Again, this is fixed by my choice of this theta function previously. So this is just defined if I have a formal series. So the Q Borel transform takes in formal series, spits out formal series. And so I just take this formal series and multiply each term by a quadratically growing power of Q. And it's weighted by this kappa here. And so if Q is less than 1, of course, this makes the series much, much more convergent. And so then to define a Q Borel resummation, we need an inverse operation to this. And here so this is given by a Q Laplace transform. And so the Laplace transform, as opposed to the Q Borel, takes in functions and spits out functions if they're convergent. And so here it's defined just as this sum of the ratio. So we evaluate f at some particular points, and we divide by a theta function evaluated at the same points, summed over this lattice. And so this lambda appearing is, you should think of as some analog of Stokes. It's some kind of Q Stokes phenomenon, the fact that this lambda appears in the Laplace transform. And so here you can see easily in this definition that this lambda, if I multiply lambda by Q, so if I do a shift instead of in X in lambda, this sum will remain fixed because it just shifts the index. So this lambda appears as some elliptic variable that's sort of additional information. This should capture some, be related to some kind of Stokes phenomenon. Okay, but so for Borel resummation, the basic property we need is that these two operations are inverse to each other on polynomials. And so that you can check. And it's a very easy little calculation here. I mean, you just need to check this on x to the k, of course. And so once you check that, then of course that proves this by induction. Okay, or not even, okay, let's say by induction. Okay, so then just a quick aside before I go on. As I mentioned, this lambda appearing should be related to this sort of so-called Q Stokes phenomenon. And earlier this year, me and Stavros wrote a paper where we sort of looked at this in some examples coming from knots. And normally this Q Stokes phenomenon is a little mysterious, but in these examples coming from knots, we can actually sort of really compute things. And so what I mean by that is, before I gave you sort of the ansatz to solve the difference equation around x equal 0, we can also apply Frobenius method sort of to the top of the Newton polygon and get a solution around x equal infinity. And then I can construct two Wronskians, again, as actual functions using Q Borel resummation. And I can take their quotient. And this is the so-called monodromy matrix of the difference equation, or the Birkhoff matrix. And this, so calculating this matrix, you can see, this M should depend, of course, on mu and lambda. So the mu and lambda appeared for however many, this could be a sort of vector of different elliptic variables, depending on how many Laplace transforms we have to use. But so calculating this monodromy matrix is an interesting problem from like the Galois theoretic perspective of these difference equations. And so in examples, you can actually compute this. So the simple operator I gave you before actually appeared in work of Svegas in his thesis on mock theta functions. And here you can explicitly compute this monodromy matrix. And in the paper with Stavros, we looked at this for some interesting examples coming from knots, and you can do similar sort of calculations. But that's just an aside. So the point is, if I give you a difference equation, I can find solutions that are meromorphic functions for q less than 1. Okay, so now we want to shift to 3 manifolds and what kind of, how they're related to difference equations. So where do these difference equations come from for a 3 manifold? And so this goes back to Jones's discovery of this, his polynomial invariant for links. And then Witten interpreted this famously at the end of the 80s in terms of quantum field theory. In particular, Witten wanted to consider a sort of formal integral of this sort, where we integrate over connections, SU2 connections on our 3 manifold, and we take some sort of exponential integral weighted by this Chern-Simons functional. So the Chern-Simons functional for one of these connections, if I view A as a connection 1 form, I take this particular combination, I take a trace, I integrate over the manifold, and so this gives me a functional from connections, and then I integrate over the space of connections modulo gauge. Unfortunately, this making sense of this integral is quite hard, but Witten sort of plays with formal properties that come from this, and really has a lot of, and introduced a lot of insight into how we could potentially define mathematical theories related to it. But so one issue, just a little issue initially, is that this Chern-Simons invariant is only defined up to 2 pi I squared times integers. And so for this integral to even make sense, you need some sort of fixed quantization of your parameter h bar in your theory. Okay, but so Witten takes this and sort of looking at formal properties this quantum field theory satisfies, constructs the Skane relations that kind of determined the Jones polynomial. And then sort of gave us a big general hope of different theories that should come. So in particular, for instead of just the Jones polynomial, we want a sequence of polynomials for each n for a knot or a link. Okay, and so then that's sort of the mathematical thing that we want. But at the looking at this integral from the physical side, it's important to note that sort of the critical points of this integral are given by SU2 flat connections. Okay, here I've run SL2C, but yeah, this should be an SU2 at the moment. Okay. Yeah, so Witten sort of introduced many of these ideas, and then Reshtikin and Churayev sort of realized this mathematically using quantum groups. And so in particular, they took quantum SL2 and used sort of Drinfeld's R matrices as sort of the basic building block to construct invariants of links. So I'll give you the sort of the main ingredients here, but this is just so you can see the sort of the shape of the equation. So in particular, for a link, we label components of the link by some integer, or you can think of this as some vector space. So yeah, some representation of this quantum group. And then there's some sort of capping operation. So if I have a cap and a cup, there's some thing that you need to, some sort of endomorphism you need to add to that. And then finally, for sort of a crossing in your link, you want to look at this R matrix, which sort of does some braiding. And so in particular, why I want to show you this R matrix is because it's of this particularly nice form. So in particular, you can see it's just a product of Q to some quadratic form with some constants, and then multiplied by a ratio of Pochhammer symbols. And so in particular, this R matrix for SU2, SL2C is related, it's Q hypergeometric. And so this is going to determine a lot of the properties of these invariants when they're constructed. Okay, so this was just very vague, but so this is sort of how a calculation would go. So as I mentioned, you can see at the top of this thing, there are these 2 caps. I hope you can see my cursor, maybe not. And here, they have some operator E attached to them. If you have just a single strand along, you just include the identity. And for these crossings, you insert an R matrix. So for a knot, you take some representation of this form. So this is as a sort of tangle. You can also do it sort of in terms of braids. and you consider some endomorphism that you build up locally from little bits. So you can imagine this is sort of like, it's similar to, yeah, Witten's ideas somehow relate these quantum field theory constructions to Morse theory. And so these sort of little pieces are sort of the critical points. So this is where the interesting stuff is happening, and you're sort of adding, you're building up locally these operators in terms of, yeah, just the local pitches. So, okay, so this is sort of how a calculation would look. And in this particular example, if you close this, then this operator, you want to take some trace. So if you sort of glue the top to the bottom, as if it came out of the board, say, then this would give you the figure 8 knot. And if you do this computation and you use some simple identities, you can actually calculate this colored Jones polynomial. In this case, is given by this nice hypergeometric expression here. And so this was first calculated by Ley and Habiro independently. Okay, so this is just an example. But so the fact that this is Q hypergeometric allowed Gareth-Leeders and Ley, using Zalberger theory, to prove the existence of a recursion for these colored Jones polynomials. So using a few initial values, you can calculate this colored Jones polynomial just from, the second, third, and fourth, for example, depending on the order of the recursion. And so, as I said, this follows from sort of the explicit Q hypergeometric expression from the R matrix, and then a lot of other details you have to check, of course. But so here, the Weyl algebra acts in this way. Instead of multiplying x by q, you just shift the n, this color, by 1, and multiplying by x is now multiplying by q to the n. Of course, you can see how they're related. And so, yeah, they proved the existence of some operator that annihilated this sequence. And this operator was called A hat. And this was called A hat because prior to the proof of its existence, it was conjectured this operator existed and that its classical limit should give rise to this SL2C character value. So in particular, it should give rise to the space of flat connections, SL2C flat connections on the knot complement. And so this is now called the AJ conjecture.
So I'm a bit confused. The quasi-classical limit, does it know what n is? I mean, it's rather a question about the Homfle analog.
Yeah, so the classical limit here, I'm being a little vague. So you replace q to the n by x. You replace the shifting operator by y. So every time you see a signal, you replace it by y, and then you set q to 1. So you can think in terms of the Weyl algebra, you basically just take the polynomial in sigma and x, and you set q to 1. And this will now be some commutative polynomial, and then this commutative polynomial should cut out a variety, which is isomorphic to this space of flat connections.
Yeah, it's 0 for the A polynomial.
Yeah,
Yes.
exactly. When that equals 0, that's right. Exactly. Mm-hmm. Yeah.
Mm-hmm.
And Campbell, I guess it's not really the moduli space of flat SL2C connections, right? It's the image in the, characteriety of the boundary that it sees.
Yes. Yeah, exactly. Yeah. Mm-hmm. Yeah. So you map sort of to two particular, in terms of the matrices, in terms of, I showed briefly that these flat connections, I don't think I said it, I just had it on the slide, is related to representations of the fundamental group. And so the two variables that appear in this limit are, related to some eigenvalues of two particular matrices, corresponding to the image of boundary curves on the knot. Exactly. Mm-hmm. Okay. So, if just to see an example, for the figure 8 knot, it looks something like this. So you see that this is a second order inhomogeneous recursion. And you can make this third order, of course, by homogenizing. You just take an operator which annihilates this, the inhomogeneous part, and just act. Okay, but if we look at just this homogeneous part of this second order inhomogeneous equation, and you do this substitution that I mentioned, then you see this polynomial here, and this was calculated by Cullershalen and others for their original, in their paper where they calculated these A polynomials for a bunch of examples. And so this is some component in this image that corresponds to some sort of, it contains some sort of geometric representation, let's put it like this. Okay, So that's a story for, that's where difference equations come up for not complements. And so then, yeah, so now we want to shift towards closed manifolds. So yeah, going back, we have now this sequence of colored Jones polynomials for a link. And in Witten's article, he suggested a way to use these colored Jones polynomials and some kind of surgery formula to construct invariants of closed manifolds. Now they won't be polynomials, they'll be just functions at roots of unity. And so to do this, we can use this following theorem from topology. So in particular, every closed 3 manifold, you can construct this by taking a link in S3, in the 3 sphere, and then gluing a bunch of solid tori into the complement of that link with some particular mapping class group representations. And the mapping class group of the torus is just SL2Z, and these gluings are even just determined by sort of the ratio of the 1,1 and the 2,1 terms. Okay, and so then Reshtikin and Shrayev sort of took this idea and just gave explicitly what this formula should be and proved that it was an invariant of the 3 manifolds, because these particular presentations of 3 manifolds, there's a bunch of basic moves that relate them called Kirby moves, and they just take these representations and just show that this formula that they give here is invariant under the Kirby moves. And so here, if we fix a root of unity, so A and C as some coprime integers, then this is defined in the following way here. So you can, this prefactor is just taking care of some kind of normalization. So this bottom line, that's sort of the main content. And so here you see this colored Jones polynomial. And then we see this product of quantum numbers. So this q to the n on 2 minus q to the minus n on 2 divided by the corresponding things with n equal 1. And you can think of this, the reason this is coming from a surgery formula is this colored Jones part corresponds to the link. And then this term here, this square of these quantum numbers corresponds somehow to the torus that you're gluing in. Okay, and so then we have invariants of 3 manifolds. So if I give you a root of unity, you get some number that's spat out for the given 3 manifold. And so these are these WRT invariants. Okay, so
what is A in the formula? I'm kind of confused because you presented the root of unity in so complicated way that there is A, there is C. So what they are?
Yeah, so A and C is just some rational number. And I just fix a 4th. So for any rational number, I get a root of unity just by taking e to the 2 pi I times that rational number.
Your sigma L, what depends on A in the answer? I'm just looking at the formula.
Just Q. Just Q.
Just Q. It's just...
Okay. Yeah, so you see here that C appears. So the denominator, you sum the number of terms that correspond to the order of the root of unity. This sigma, this sigma, I'm being vague. I said, you can kind of ignore this first term in some sense, but this sigma is related to some eigenvalues of the linking matrix of this particular link. And this little L is the number of components of this link. And so this factor you can determine by basically, if you cut out a solid torus and glue it back in, you want it to be the same manifold. And so this prefactor determines that. So if you just, if you take an unlinked solid torus, cut it out, glue it back in with no particular mapping class group, just as it was, then you want this to be the same manifold. And this deals with that in some sense, some kind of normalization. Okay. Yeah, so in an example, so the example that I'll try and talk about mostly today is this half surgery on the figure 8. Sorry, there's a minus here, but these two are just the same because of some symmetries of the figure 8. So sorry, just ignore the -1 in the text. So Belyakov and Leh proved the following nice formula for this. So in particular, they give some nice presentation for this WRT invariant for homology spheres. And this manifold is a homology sphere, integer. And they give this formula from a particularly nice presentation of the colored Jones polynomial. And so here, this is just the outcome of this. And so again, this is nice and Q hypergeometric. This is actually an element of the Hibiro ring, if you know what this is. So here you can see this this ratio of Pochhammer symbols on the right is actually just a polynomial. So these denominators never actually occur. They always cancel with terms in the numerator. So there's some Gaussian polynomial times a shifted Pochhammer. Okay, but so it's Q hypergeometric, and so I can just construct, just looking at this formula, I can take this family of WRT-like things. So here I'll just denote F to indicate that it's somehow just different, and it just comes from this particular expression. So this is some sequence of new functions from roots of unity, but it's not necessarily clear that this is canonical in any way associated to the manifold. It just comes from this formula. But we can look at this sequence and look at kind of recursions that it satisfies. And indeed, it satisfies a recursion, just like the Color-Jones polynomial. And so this defines some non-canonical module associated to this difference equation. And so here I can also take the classical limit. So you see it's a 7th order inhomogeneous. And again, if I set, these n's should be 0. Sorry about that, in the equation. So if I set q to 1, q to the m, I also set to be 1 in this case. Just look at the shifts as powers of z, then this will give me a degree 7 polynomial. And in this case, this degree 7 polynomial defines a field with 1 pair of complex embeddings and then 5 real. And this field is actually determining the set of flat SL2C connections for this manifold. So here there's a finite set of flat SL2C connections up to gauge, and they're given by, they correspond to points on this on this variety or this field. Sorry, Jan, what was your question?
What variety? On what variety?
On this, just this set of points, this field.
So connections on the set of points.
This is what.
Complete.
No, Campbell explained. You have this for one knot and make 1 to surgery, so you get closed manifold.
Yes. Mm-hmm.
Okay. Okay.
Yeah, sorry. So the flat connections on this manifold, this, yeah, exactly, this 4-1 where you've glued in solid torus with a twist. Okay. Okay, so now I want to talk, so that's sort of the story at roots of unity, and that's more classical. But now I want to talk about Q series that are more recent. So in particular, Gukov and Manolesco constructed, or they give some evidence for a 2-variable series that depends on an X and a Q that should correspond to knots. I mean, I guess it should correspond to links, then you'd have more variables, but for knots, you want, yeah, just these 2 variables, X and Q. And so in particular, they want this to be some kind of resummation of Vassiliev invariance. That I'm not so sure how it sort of, it's not clear exactly to me what kind of resummation is happening, because I don't, but regardless, they give a concrete way of computing this using the A hat operator. So from a knot before, we saw that the Color-Jones polynomial satisfies a recursion, and this gives me this A hat operator. And so I can take that operator, and instead of, I mean, I have this Color-Jones solution, but now I can just take the A hat operator and look for solutions now in Q series. And if I fix some initial conditions, then this will determine the Q series as a power series in X at least. And so the fact that the A polynomial, there's always some component of this A polynomial that corresponds to trivial connection. So that means in the Newton polygon, there's always going to be some flat edge. And if we have a flat edge, that means that we can always find some solution in power series corresponding to that flat edge. Because it's flat, there'll be no theta function corrections or anything like this. So we can always find a power series solution here, and this is sort of what they take. And this is, yeah, I mean, this gives a concrete way to calculate it. It doesn't necessarily prove that it's an invariant, but I mean, because of course, you know, we have a basis of solutions, but okay, there's an algorithm to compute this thing. And so recently in work of Park, he gave a formula for this. We actually came up with it independently and then found Park's work, which beat us by 6 months or so. But so it's again some nice Q hypergeometric function. And this is actually, if you squint very hard, you might be able to relate this back to the formula of the original Color-Jones polynomial of this particular knot 4-1 that I gave previously. But okay, so there's some particular Q series Here, there's sort of some anti-symmetrization that's happened. So we see these negative powers of x as well, but you can just think in terms of the first term in these 4 x's keeps track of somehow the solution. And then the rest is normalization. And so previously, around 2010, Garofalidis and Zagia found a sort of related series, which you can think of as some particular specialization, say to x equal 1. You can't just substitute x equal 1 here, but they found some series that is related to maybe taking a residue around x equal 1. So here will be some pole, but okay, you can still, yeah. So anyway, this came a lot earlier, and this is, yeah, this has some nice properties that we'll see in a second, but it's sort of a specialization of this 2-variable series. And this is related to holomorphic blocks that were investigated by Beam, Demotta, and Paschetti in the mid-10s. Okay, so that's the story for knots. And for the closed manifolds, yeah, Gukov and collaborators expect to get series like this G. So there's no extra parameters, there's no boundary for a closed manifold, and so we should just get some Q series. And they also want this indexed by spin structures, but okay, in the example we'll look at, it's an integer homology sphere, there's just one. Okay, and they want this to be some kind of categorification of the WRT invariant. Okay, so but still there's no mathematical definition, but they give a concrete way to compute this. So using this 2-variable series that they construct and sort of an analog of the Belikov-Ley Laplace transform, they give a particular method. So if I take my knot and I look at the 2-variable series, and then I want to perform some rational surgery on it. So I twist around in one direction of the torus by P and the other direction by R. Then I can consider some particular Q series that you get by sort of taking this formal Laplace transform. So at each stage in each power of x, I just replace it by this particular combination here. And then I just look at the formal series and then just sum up all the terms. It might, I mean, it's not necessarily clear that it's convergent, but okay, I get something. And so in the work for my thesis, I was looking at this WRT invariant, and I considered sort of an associated Q series. And so in particular, in some sense, I solved this non-canonical module in Q series with the normalization that came from the WRT invariant. And so I constructed some Q series. It looks like this. These are the first few terms. And this ends up agreeing with this computation of Gukov and Manolesco. But here we see a particularly nice form again. It's sort of this nice Q-hypergeometric expression. Okay, so now we're going to start. So I've sort of given you the full story of all these invariants. And so now I want to talk about their asymptotics. Okay, so what we have originally, we were sort of looking at roots of unity, and now we're pulling these into Q series using sort of solutions to difference equations that are associated to the original invariants at roots of unity. Okay, and so now we can look at their asymptotics as we send Q to 1. So from Witten's original definition, this exponential integral, we'd hope to be able to apply some stationary phase. If the integral was finite dimensional, of course, we could do this concretely. But we can still hope for something like this based on Witten's intuition. And so in particular, for the WRT invariant, when we have the closed manifold, we'd expect, as we send h bar, so if Q is e to the h bar and we send h bar to 0, then we expect to see asymptotics of this form. So we expect to see a sum of SU2 connections, the sort of action associated to each of those, the classical part with this exponential growth. And then we want some full asymptotic series that are attached to each of those. And so this, which would just follow if the integral made sense, becomes a conjecture, and it's known as Witten's asymptotic expansion conjecture. Okay, so that's sort of the original version. And then in sort of mid-90s, Kashayev constructed an invariant for links. And the way that he constructed the invariant made it very suggestive that the asymptotics of his invariant, so it's an invariant that takes in roots of unity and spits out numbers. And the way he constructed it made it look like it should see the volume in the exponential. So instead of these Chern-Simons things here, which for SU2 connections are just real, so these are just oscillating. Sorry, I might have said exponential growth before, I hope not. But, these are just oscillating terms. But so Kashayev's invariant, it looked like this should be related to the volume of the knot as opposed to these oscillating terms, so exponential growth in relation to the volume. And so then around 2000, Murakami showed that Kashayev's invariant was actually just a specialization of the Color-Jones polynomial, kind of like setting x equal to 1 that we saw for the Garofalidis and Zagier series. And so then this gave the following conjecture for the Color-Jones polynomial. So if I evaluate the Color-Jones polynomial at a particular root of unity corresponding to the color, so this the primitive nth root of unity corresponding to n as the color, and we send n to infinity, then this should grow exponentially like the volume, the complexified volume, and then there should also be a full asymptotic series here. And so then in work that followed this, Demofta, Garofalidis, Gukov, Kami, and Lennels, and Zagier gave constructions of this asymptotic series using triangulations. So although I don't think those, so just the sort of the first couple of orders of those asymptotic series are proved to be invariants, but the rest are conjectured, and in many examples they seem to match. But okay, so there's a definition for these asymptotic series in some sense, conjecturally. And so you can see this SL2C sort of arising because we can think of the SU2 connection inside this space of L2C connections. And then sort of when we do a stationary phase, of course, if I do a stationary phase of a real integral, it will see complex critical points as well. So you could think maybe there's some analogy here where we're sort of, these other critical points are appearing because of they live inside this bigger space. But again, these infinite dimensional integrals, I don't have the best intuition, so there's probably people here with a much better idea about how this goes, but this is how I think about it. Okay, so then much more recently, sort of in the mid-10s, around 2016, Chen Yang gave a version of the volume conjecture for WIT invariant. So originally we saw that if we evaluated at these particular primitive roots of unity, we want some polynomial growth. So it should oscillate a bunch of oscillatory terms that are all related to SU2 connections. And so what Chen Yang did is they looked at, instead of just the first primitive root of unity, the nth primitive root of unity, they shifted this by a half. And then when they did this and looked at the asymptotics, they saw again this exponential growth determined by the volume of the manifold, the hyperbolic volume of the closed 3 manifold. And so here, this now gives us some sort of analog of the volume conjecture for closed manifolds. And this is proved in a bunch of examples. And so in particular examples we saw before. So yeah, as I said, compared to Witten's asymptotic expansion conjecture, we saw some polynomial growth, but here we see exponential growth. Okay. And so if in our previous examples, we can look at the figure 8 knot again, is 4-1. So here the volume looks like this. And so many people, Anderson, Zagier, Hansen, and many others, proved versions of this. So in particular, this does indeed grow like the exponential of the volume of this particular knot complement. And then we see some sort of polynomial term and then a full power series. And this power series is defined over square root of -3. And this corresponds to the basically the flat connection that corresponds to this geometric structure. This flat connection is defined over square root of -3. So these asymptotic series know something about the fields that these connections are defined over, if they are defined over fields. And then the remarkable observation of Garofalidis and Zagier when they discovered this series and realized it was related to 4-1 because it came from somewhere completely different. But they realized that if they took the asymptotics of this Q series as they send, now tau is in the upper half plane. And so this is now exponential of 2 pi r divided by tau. Sorry, it's maybe in the lower half plane. Sorry. This now is some Q less than 1. It's some Q series. And if we take Q to 1 in this, for this Q series, we see exactly the same asymptotic series arise. There's a shift in weight, but okay, the same asymptotic series arise. So basically a similar thing will happen for the closed manifolds. So in particular, this half surgery on 4-1, this particular closed manifold, it had the 7 connections that I mentioned that were defined over this field. And it and then has one extra one that corresponds to trivial. So the non-trivial connections, we have a bunch of, so these are all their Chern-Simons values. So in my indexing, row 1, row 2, row 4, and row 5 are all SU2 connections, and row 3 is an SL2R connection, and then row 6 and row 7 are SL2C connections. And so there's a bunch of, so these are their different Chern-Simons values on the left, and then this is the generator of the field on the right, and in the middle is some sort of, in the quantum, in these asymptotic series, these correspond to sort of one loop invariant. Okay, but so then we can look at the two conjectures we have for the WRT invariant in this case. So Witten's asymptotic expansion conjecture was studied a lot by Anderson and Hansen, and then later it was proved in this example by Charles and Marchais to leading order, just to leading order. And so here, as I said, the connections correspond to 1, 2, 4, and 5. And this is a plot of the WRT invariant for the first 100 integers when I take Q is e to the 2 pi I divided by n. And so then I can compare this with the leading order expected by Witten's asymptotic expansion conjecture. You see it matches up very nicely. So, I mean, this is just leading order. So these pictures are very misleading because, yeah, I mean, it only agrees to a couple of decimal places, but okay, it's kind of, it looks quite nice that we get exactly this lineup as we expect. It's proven, so that's good. Okay, so now for the Q series, so now if we take these shifted roots of unity, then we see exactly the exponential term we expect from the Chen-Yang volume conjecture. And this was also proved quite soon after they did it in this case by Otsuki. Okay, so we see, as we expect, this exponential growth when we take these second primitive roots of unity for odd order. And now if we take the Z hat invariant, we see exactly the same thing. So the Z hat satisfies a similar version of the relation that the Garofalidis-Zagier series before one saw in relation to the Kashaev invariant. And so again, if we take Q less than 1, sort of on a strong angle heading to 1, we'll see that this we'll see this exponential growth, and we'll see a full asymptotic series, and the asymptotic series will agree. I haven't written the terms here, but you can compute them explicitly, but they're defined over this degree 7 field. So it gets a little messy to write, but now if we look, instead of sort of on a small angle near the reals, if we look at sort of directly going radially, so sending Q to 1 radially from 0, we see some other kind of exponential growth. And here we see the SL2R connection appearing. And so this exponentially blows up, which is a little surprising because this gives a counterexample to, and this happens at all roots of unity. So I'm sending Q to 1 here, but you can send Q to any root of unity and you'll see this exponential growth. And so this gives some kind of counterexample to a conjecture of Gufov and Manolesco, where they wanted these Z-hat invariants to take, if you take the limits, they should give you just back the WRT invariant. But in general, this seems not to be the case. However, I mean, it's not really that bad because although the limit won't exist in this example, we saw these asymptotic series actually know about the manifold. So instead of having explicitly the WRT invariant arising as a limit, we get some asymptotic series instead. And so their conjecture holds in cases where if the dominant term is the trivial connection, so it doesn't have any exponential growth or anything, and a trivial connection will just, to leading order, see the WRT invariant. If that is the dominant term, then of course their conjecture will hold. But in general, we'll see more interesting asymptotic series arise. And that's potentially fine. So it's not a big deal. And so the last thing I want to say on asymptotics is that we can actually lift this to many more terms, to more accuracy when we take these angles using this quantum modularity. So in particular, at roots of unity, it's very nice. So if instead of taking these integers that we were taking before and we take rational numbers, we'll see exactly the same asymptotic series arising, but we'll see some correction term appearing out as some, for roots of unity, it just looks like some constant. And here it's actually just the original invariant corresponding to sort of a modular transformation of the original numbers. So here you see as a correction the Kashaev invariant again. And similarly here at the level of the Q series, you'll see the same thing. Oh, sorry. I'm jumping all over the place. Sorry. So for the WRT invariant, we also see this kind of modularity. So in particular, for the Chen-Yang case, we saw there was some factor of 2 that appeared out the front. And in general, if I take not n plus a half, but I take n plus some other rational number, you'll see the WIT invariants corresponding to those rational numbers appear out the front here, multiplied by the full asymptotic series we saw. And so this behavior is somehow should refer to as quantum modularity. And just how this relates back to Witten's asymptotic expansion conjecture, with this particular normalization of the WIT with the 1 minus q out the front, we see that when q equals 1, so when we look at the roots of unity that Witten was considering, we get back the sort of constant term that corrects the asymptotic series is just 0 in this case. And so then we don't see the geometric connection appearing. And then what this is sort of, I mean, if you wanted to make this quantum modularity conjecture, this would say that, you know, to leading order, it's the growth of the WIT invariant as q goes to 1 through rationals is, or through those special rationals where it vanishes, is exponentially smaller than the volume. So it's a lot weaker than Witten's asymptotic expansion conjecture, but you can kind of unify them in that way. And then the same kind of thing happens for Q series. So if we take Q just above the reals, then we'll see that Q tilde now will be very close to 1 because it will almost be a root of unity. And then you can actually see, just when you do calculations of the asymptotics of these Q series, you'll see Q tilde terms appearing, because now they're not exponentially, I mean, they are exponentially small when you really get to 1, but for a finite Q, you will see these Q tilde terms appearing. And you can actually, you see exactly the same thing coming out, this sort of quantum modularity for the Q series now. So instead of these just being the WIT invariant, or yeah, evaluated at some sort of modular transformed root of unity, we see the modular transformed Q series appearing. But it's completely analogous, so exactly the same thing's happening. And this is the same for the Z hat when we take this very strong angle. Okay, so I'll try and, in the last 5 minutes, give you an idea of what's going on for the Borel and Stokes computations now. So I've set it all up. We have these asymptotic series, we have this quantum modularity.
Campbell, I think you started 5 minutes late, so you have certainly 10 minutes.
Okay, great. Then I think that should be all I need. Okay. So yeah, so we have all these asymptotic statements, but we would like to lift them now to really statements about analytic functions. Okay, so and to do this, we want to resum these asymptotic series. So if we have a divergent series, or if we just have a formal series like this, so say f of x is some formal series, now we can take a classical Borel transform, so none of this Q Borel, but a classical Borel transform will just be, you take now this formal series, you turn it into this formal series where we've divided each of the coefficients by the gamma function corresponding to the powers of x. Okay, so obviously you don't want lambda to hit a pole of gamma, but okay, so let's assume this isn't the case. Okay, so now if this function is convergent and has an analytic continuation sort of all the way to infinity with certain growth, then we can take its Laplace transform, so if it's convergent. And then when we do this, if we start with a formal series, we apply its Borel transform, now it's convergent and we can take the Laplace transform, and then we apply the Laplace transform. This will give us some analytic function in x. And if we take the asymptotics as x goes to 0, from Watson's lemma, this will give us an asymptotic series which corresponds to the original formal series that we started with. Okay, so this is one prescription for taking divergent series and turning them into analytic functions. Okay, and so we can apply this to all of our examples. We have all these divergent series, these asymptotic series appearing. They all conjecturally look factorially divergent. And conjecturally we can conjecturally they're Borel resummable, so we can take their Laplace transform. And you can do this numerically. And then if you compute, then what you notice is instead of the WIT invariant just asymptotically looking like the geometric term for most roots of unity multiplied by the modular transformed WIT invariant, you see now if you subtract off that leading order with the Borel resummation, now it's an analytic function, so we can subtract that term away. Then we see sub-leading terms. So we start seeing exponentially small contributions, and we see all of the other asymptotic series that correspond, in this case, to just the Galois orbits of the original asymptotic series. So our original series was defined over a degree 7 field and has a bunch of Galois orbits, and you start seeing all of these other Galois orbits appearing with their own little prefactor, some other modular functions appearing. So these omega k are just something you compute numerically, and they behave very much like the WIT invariant originally. And in fact, you can identify them mostly. So you can identify them numerically as elements in this particular module that I considered before. So I had this degree 7 inhomogeneous module that I just constructed non-canonically for the WIT invariant. And using this and looking at elements in this, it's a 7-dimensional, or it's an 8-dimensional module, you can find these WK as elements inside this module. And so then this is sort of, you can think of the right-hand side of this equation as some dot product, or a product between, a row, a 1 by R matrix and an R by 1 matrix. And then using now the Q difference equation, we can start looking at all of these other solutions, and we can construct a full matrix version of this. So we can lift this equality to a conjectural matrix version. And so then here we see the Borel transforms, so the Borel resummation, of now some matrix of asymptotic series. And then this is multiplied by some modular correction with some weight. And so we lift this original equation to a full matrix valued equation. And I won't go into the details of how it's done. Essentially, I mean, you just look at you construct a Wronskian matrix, and you look at the asymptotics of this, and you see the same kind of behavior. But what's good about lifting this to a matrix is that it allows us to conjecturally construct a formula for the Borel resummation, because we can divide by matrices. And so then we get the right-hand side is just some function that we know, like we can compute. And then the left-hand side, we conjecture then would be related to the Borel resummation. And so you see here it's some quotient of these sort of two Wronskian matrices, essentially. Okay, with some extra little factors around. And so then if you're just interested in this right-hand side, you can understand many of its analytic properties by looking at state integrals. So these were studied a lot by Anderson and Kashayev. And so they're integrals of some sort of particular special function, the Faddeev dilogarithm. And this dilogarithm, whenever you have one of these hypergeometric expressions, you can kind of replace the summation by an integral, you replace the Pochhammer symbols by these Faddeevs, and then you have these quadratic, Q to some quadratic form, you just now take e to the integration variables, evaluate that quadratic form as well. And you consider these integrals, and you can prove these integrals give expressions of the form in this bottom right expression here. So matrices of these integrals give these expressions, and this gives you a lot of information about the analytic properties of these functions on the right of this conjectured equality. And these analytic properties, they are the kind of analytic properties you'd expect the Borel transform to satisfy. And so this gives some evidence for these conjectures, besides the extensive numerical evidence. Okay, so yeah, that's just sort of what I said. So yeah, so then in a sense, much of the computation is finding these Q and P matrices in practice. They're sort of, we know now the shape. And so then in practice, if you have this shape, you need to find these simple matrices of rational functions. Okay, so now I want to talk about a little more detail about these Borel transforms, these particular series. And so here, these Borel transforms, they're expected to have logarithmic singularities at points that differ by sort of these complexified volumes, or these Chern-Simons invariants for SL2C connections. And of course, this is defined modulo 4 pi squared. So we see these big sort of lines of points corresponding to each of these differences. And so locally around each of these points, the Borel transform of these series looks like some sort of integer, this SABK, multiplied by some exponential term, which is related to the sort of these classical actions, so these Chern-Simons values, and then multiplied by some simple exponential integral. So this is just sort of taking care of the factorial divergence in some sense, times the other asymptotic series we see for different connections at relating the 2 points A and B. And so then this is conjecturally what these functions should look like. And so then the question is, can we just calculate these integers? These are the things that are unknown, and we want to understand their structures. And so, and the reason these are interesting is because if we have these singularities and you apply the Laplace transform, if you integrate along one side of this singularity, and then you integrate along the other, your functions, your Borel transforms will jump by this factor in the bottom here. So this is just in terms of one of the other Borel transforms, okay, with the exponential factor out the front, and then this integer. So this integer is keeping track of all of the information about this sort of Stokes behavior. Okay. Yeah, so then we get, okay, so then, yeah, so now if we use this sort of quantum modularity and we compute in different regions for different arguments in tau, then we find different Q and P matrices that correspond to each of these regions. Okay, so we can compute using these conjectural identities in each of these regions. And then the jumping is now just going to be the quotient of these two matrices. So here we compute and we see that, so the first term on the right-hand side, they agree. And as the analytic continuation jumps, I mean, all of the jumping is going to be taken care of by these quotient of matrices, because these other matrices will be, we basically want to multiply the matrices of the Borel resummations by these integer factors to keep track of what's going on. And so that's all taken care of by these two matrices. So in each sector, we sort of have half of the Stokes data. And so then we can compute the Stokes jumping by taking quotients. And so here sort of is the picture you should have in your head. So for each of these Chern-Simons values, we expect a singularity with this logarithmic branch cut. And as you go across, we want to understand how the matrix of Borel transforms relates to the matrix of Borel transforms in the other. And again, the matrices are super important because we can sort of just take ratios between the two. And so in particular, these matrices will store all of these integers of Stokes data. And then because of the shift in this 4 pi squared, these integers will also correspond to some Q tilde to the K. And so then as we take products of these, we build up a matrix of Q tilde series with integer coefficients. And so if I take sort of the product along all of these rays all the way down to this going from region I to region 4, sorry, region 1 to region 4, then I get a quotient of two matrices that gives me matrices of Q tilde series, and they keep track of all of the Stokes data. And so then finally, 1 minute over. So finally, I just want to say, so you can do this for this example of the closed manifold for 1, and it's just the same kind of computations that are in these previous works of Garofalidis, and Marino, and myself in the last sequence of these papers. And yeah, in this case, you see series that look like this. If you take sort of the closest order Stokes data, you see a matrix of this form. And this agrees with sort of the computations you would do if you just looked at the asymptotics of the coefficients that arise in these asymptotic series. But here you can just really compute to all orders conjecturally. And sort of the structures are very neat, and this should work for many examples of Q-hypergeometric functions. So there's sort of nothing special about knots. You can do it for the closed 3 manifolds, and you can do it for just other Q-hypergeometric functions that maybe are not even related to the 3 manifolds. So it's really just about the shape of the Q-hypergeometric structure. Okay, so thanks a lot. And here's a bunch of the references if you're interested. Okay, thanks.
Okay, so thank you, Campbell. So are there questions? Well, let's thank the speaker. It's so funny in these
yeah, this is Zoom show.
But anyway, are there questions to the speaker?
Sorry, Campbell, do you understand that you know this completely in this example, this matrix, whatever 7, 8 by 8 matrices, this Q series of Stokes indices? Yeah. Yeah,
so you can compute it conjecturally with formulas. So you have, have geometric functions, and I have the two matrices, and there's some quotient of explicit functions. You can compute to all orders conjecturally, of course. It's all, the beautiful thing about this construction is that all of the data is stored in these kind of, these matrices P and Q, which are just some matrices of rational functions. So they're just very simple data to keep track of.
And this is in your papers. Where is this concrete examples?
These matrices will appear in my thesis, I guess. So this will be
Okay.
in a couple of months. This should come out.
Okay.
Hey, Marcos.
Yeah, well, let me congratulate you because I always dreamt of doing this example, and, but I was scared by the 7x7 metrics. So,
Yes, yeah, I can even show you the Q series if you want.
I'm very impressed. I'm very impressed. Yeah, let me make you just a kind of one comment is that actually Sergey Gukov and I were aware that this Z series that he constructed with Manolescu, it actually grows exponentially as you do radial. I mean, Sergey and I discussed at some point, some time ago, and we did some calculations, and it was clear that there was exponential growth. So, I mean, I personally didn't identify it as clearly as you did, but we were aware. And the point of view of Sergey, I think, was that, okay, that's fine. What is important is to have an environment that detects the trivial connection in some way, yes. Right?
And that it definitely does.
Yeah. So in that sense, yes, I think there is, one has to refine these conjectures, but essentially the invariant does what it should do, which is to see the trivial connection. But just one question. So you definitely have, I mean, in order to get the full matrix, you need more series than just the series that they had, right? So you have a construction. I think these are the series that you showed me here, right?
Yes, they're beautiful, but yes.
Yes. So I guess, so the series of Gukov and Manolescu is just one of them, right? Because you need
exactly.
7.
Yeah. So this is the thing this is why so this is the thing with this full matrix, you can get back the trivial connection because you can sort of take, essentially what's happening when you take these quotients is, there's sort of cancelling of this leading order that,
but you just
by taking these quotients, then you get back to you can isolate the trivial connection.
But you need more than just the Z function that they had, right? You need seven series out of them, right? And the way you construct
for this difference equation.
And then the way you do it is by constructing these Frobenius solutions for the Q difference equation, right? In that case as well, right?
Yes, exactly. Yeah. So I mean, the thing is, the only subtle point is that. Okay, so yeah, maybe I can give you like a little more detail about how this construction will go. So you start with, so essentially for this Z hat, the way that this goes, I start with my nice formula, and I want to write down a state integral as you just would. You replace the Pochammas by Faddeevs, and you replace the quadratic terms by Gaussians. If you try and do this, the state integral is sort of trapped as we experienced with 5.2. And so you can't just do the factorization of the state integral as you would like. And so then before you write down the state integral, you should apply a bunch of Q series identities to write the original series in a different form. So in fact, this first series is Z1. This is a different version than I showed you previously of the Z hat invariant. So you can see here, I pulled out a Pochhammer squared. And so once I've written it in this form, then I can write down a state integral, and this state integral isn't trapped. And then I can just factorize the state integral using this. So like the mathematical content, I mean, this is a quantum modular form in a sense. So it's really proven, the analytic continuation of these functions. So you can prove it by doing this untrapping. And so this is how I get this specific basis of solutions, because this comes from state integral. Because the normalization with the Frobenius method is subtle. It's not clear. You have to be smart about how you choose it. The state integral dictates it to you.
So you have to do some of these descendants for this state integral as well, I guess.
Yes. Yeah, definitely. Yeah.
Very good. Very good. Okay. Well, congratulations. What can I say?
Yeah, thanks.
A question here. So there seems to be 9, but so.
Yes, this is a subtlety between. So the state integrals always factor as Q and Q inverse series. And so, yeah, this Z3 and Z1. So yeah, there's some subtlety here. Yeah, exactly. So the Z3 only is good for Q inverse. And then the Z3 is actually should be the analog of Z hat for Q inverse. And yeah, because Z1 for Q inverse doesn't see the trivial connection. So there's many subtle structures associated with these things. But so when you factorize the state integral, you'll see both of these series. So you'll see Z3 for Q inverse, and you'll see Z1 for sort of Q.
Okay, I see. And which one is the conjugate of all of these?
The conjugate.
The conjugate representation. So the one that's conjugate to the hyperbolic.
Okay. So the one that the subtle point here is that, I mean, yeah, these indices, so these series, they see all of the connections. So there's no canonical bijection between these series and the connections. And so this is why, for example, yeah, like in some way, this the Z hat invariant, it knows it should know about all the connections. It shouldn't just see, even in the cases that it sees the trivial, if you do Borel summation and kill off the trivial term, you should see the other connections to exponentially small corrections. I mean, I haven't tried this for one of these non-hyperbolic examples. I mean, I tried it for some knots that are like this, and of course the whole story goes through, but I mean,
there should somehow be some kind of expression which should be exact, right? Which sums over contributions from each connection.
Yes, exactly. And so that's when then there's a subtlety with this. It's related to this modularity. So like it's kind of in this P and Q matrices that I had. I mean, you need to find the particular basis in each of these regions when you do Borel summation, and finding that basis changes at each stage. But for a particular region, you have, yeah, a set, in this case, of 8 canonical series that are associated to each of the connections. But that changes, that depends on the region.
Yeah, you're right.
Yeah,
sure. Yes, great. Further questions?
Yeah.
Stavros?
Oops. Yeah. So is it fair to say that for a closed hyperbolic manifold, like the integer homology sphere you studied, the 3D index of it is actually not a single Q series, but in fact, an 8x8 matrix of Q series. Unlike the case of knot complements, where the 3D index is an integer by integer matrix of Q series.
8 by, yeah, in this case, yeah, it depends on, I guess, I mean, these Stokes indices, yeah, as you know, should be related to what the 3D index should be for this. But I mean, yes, there definitely should at least be 8x8. I mean, the thing is, you might be able to, I mean, we have this full module of these series, and if we don't necessarily just care about our 8, we can of course take a full, we can consider all the different elements of this. And then maybe you can get the Z by Z. Yeah, I'm not sure. I have to think about it a little more. But
thank you.
Yeah, no problem.
More questions? No? Okay, well then let's thank Campbell again.
Thanks again.
And thank you for your talk.
Yeah, thanks.
Okay. See you guys.
See ya.
Thanks.